Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Good day, everyone. So we are in the middle of talking about continuous random variables, but before we do that, I'm going to duck back a little bit to last time, because there was at least one person who has felt I hadn't said everything about the Poisson, which is true. I haven't stated the probability mass function in class, although it was on the tutorial one week. But I'll just review a couple of things about the Poisson before we go back and do more about continuous random variables. So let's get onto Poisson lambda. You just remember last time I said we're thinking about rare events that can happen over time, but whether an event happens in one period of time is independent of whether it happens in a disjoint period of time. If that's the case and you're just counting events, then it turns out that you have to have a Poisson distribution. So is the limit, that x has the distribution Poisson lambda, limit as n goes to infinity of binomial n comma lambda over n. So you could break your time period into n equal subintervals. Each of them would have an expected number of occurrences of lambda over n. And if you make the subinterval smaller enough, the chance of having two events in the same small subinterval is negligible. It's like if you're running a shop, the chance of two customers entering in the same millisecond is negligible. So that's the principle. We just divide it up long enough so that we can ignore the possibility of having more than two of these rare events within the one subinterval. Once you have that, it's easy. But let's just define the probability mass function of x. We're just going to do it as a limit, exactly as suggested. The binomial mass function n choose x. Now, I guess last time I said k because k is a number, but nevertheless, x can only take the values 0, 1, 2, 3, and so on. It's a counting variable, so it could be 0 if nothing happens, but it can't be a fractional number. N choose x, so for p, which is lambda over n to the power x, and then 1 minus p is 1 minus lambda over n to the power n minus x. So we're just going to do a calculus exercise, or something that should be familiar from maths to do this for you. We'll have n times n minus 1 all the way down to n minus x plus 1, because remember we have to have x terms on the numerator and n on the x terms on the numerator, x on the denominator, and this once again lambda over n to the power x, 1 minus lambda over n to the power n minus x. Now I'm going to, this is once again a limit still, n to infinity. I'm just going to do some things that, the first thing about a limit, I've got all these x n's in the denominator here. All of these things are approximately of size n, because if x typically won't be too big, it'll just be a fixed size. N is near infinity. So these are all approximately of size n. I can make that more explicit by bringing the n's into the numerator. That's 1 minus 1 over x, 1 over n, sorry, everything's divided by n. 1 minus 2 over n, and then the last one is 1 minus x minus 1 over n. So those are all the things in the numerator. Denominator is still x factorial. Lambda to the power x. Now, everything that doesn't have an n in it is pleasantly unaffected by the limit. 1 minus lambda over n to the power n minus x. So we're going to take the things that are totally unaffected, lambda to the x divided by x factorial, out of the front of the limit. Now, what about each? The key thing here is that x is fixed in the limit as n goes to infinity. I'm talking about a fixed number of target arrivals, maybe 10 arrivals, that I'm dividing into a huge number of sub-intervals, which is n. So x is fixed. So of course those come out the limit, and there are only x factors here. And what is the limit of each of these factors in the numerator as n tends to infinity? Just think of x as 10 or something, 20. Well, 1 tends to 1. What about 1 minus 1 over n? N is tending to infinity, so this factor tends to 1. Yeah, they all tend to 1. It doesn't matter that you've got an x there, because x doesn't change as n gets very large. So they're all 1. And the only thing left in the limit, it would be different if there were infinitely many factors hit there, but there are not. We've got 1 minus lambda over n to the power n minus x. I'm actually just going to put the power as n. Once again, the minus x is an irritation, because it's only an infinite number, or it's a number, it's a power that tends to infinity that is the problem. If the power is fixed, like x, then it's 1 to the x, that's 1. So it's only when you have 1 minus lambda over n to the power n, that's something where you've got a tension between one thing that's pulling one way, the lambda over n is tending to 0, and one thing that's pulling the other way, you have a very large power. There's a tension between those two. It's a classical result from calculus, and I think I might have even mentioned it before in this class, but can someone tell me the limit of that? It's got a natural exponential limit. What is it of the exponential of? Minus lambda. If you had 1 plus x over n, that would tend to e to the x. That's a classic limit. 1 minus lambda n, that goes to e to the minus lambda. You might remember this in the context of compound interest, where minus lambda is maybe a depreciation rate over a year, and then if you do instantaneous depreciation instead, you would get 1 minus lambda over n to the power n. That would be instantaneous compounding. If it's plus, then you think about compound interest, although nowadays there's negative interest rates, so you could even do this for negative interest rates. Nevertheless, that's an instantaneously compounded thing. It becomes natural exponential e to the minus lambda. So you would expect that this, so by the way, what are the possible values of x? To remind you, 0, 1, 2, and dot, dot, dot. You would expect that this sum, x equals 0 to infinity. So x is a discrete variable here of lambda to the x over x factorial e to the minus lambda. You would expect that that equals 1, and indeed it is, because e to the minus lambda is a common factor. Sum x equals 0 to infinity, you should remember from your calculus class, lambda to the x over x factorial. That's a classic, probably the choice of x as the index here was not the best letter, but anyway, that's the standard sum for e to the lambda, e to the minus lambda times e to the lambda. So that does equal 1. So check, this is a valid PMF. Remember, to be a valid PMF, all you need to say is that the probabilities sum to 1, and that they're all non-negative. They're certainly all non-negative. And then the fact is, if so, the expected value of x is lambda, and the variance of x is lambda. Now, it's true that I only sort of justified that loosely by reference to, I only justified it loosely by reference to the limit of binomials, because NP is equal to exactly lambda. N times lambda over n is exactly lambda. And NP 1 minus P is lambda times some factor that tends to 1. So that variance should also be lambda. Technically, that's not a proof. So if we wanted a proof, I think this is a good way to do another exercise in MGS. You don't have to do it as an exercise in MGS, because you could just do it directly from the definition of mean and variance. But let's do the MGF mx of t. To remind you, that is always the expected value e to the tx. That is just definition of MGF. Now, in a discrete context, I have to sum over all possible values x equals 0 to infinity. The possible values that e to the tx takes are e to the t lowercase x. Remember, when you're doing expectation of a function, you do the function times the PMF. The function is e to the tx. The PMF we've already got up here, lambda. So, by the way, in case anyone missed the PMF, here it is. Here's your PMF. And by the way, lambda is called the rate parameter. But if you're doing this over a period of, say, 10 hours, you want lambda to be the expectation. Lambda has got to be whatever it is, so that is the expected number of arrivals. That is the expected value. So, if you have lambda, if instead you have mu per hour and n hours, then it would be mu times n would be your lambda. So It's just the expectation. E to the tx times, I have to plug in this thing, lambda to the power x divided by x factorial, e to the minus lambda. Okay? Those are the possible values. Now, that you always look for algebraic simplification, so there's e to the t times lambda, sum x to the 0, infinity, e to the t times lambda, all to the power x. You see that? E to the t lambda, all to the power x, divided by x factorial. I'm going to take the e to the minus lambda out the front, because that's common factors can always be taken out the front. And that will... common factor can be taken out the front. It's a bit of a thing that we've seen again and again. E to the minus lambda. And then what about this sum? Does that look familiar to anyone? Once again, it's over all x's that are 0, 1, 2, 3, 4, 5. Non-negative integers. So it's a sum over... This is a very standard kind of a power series. You're probably more used to seeing something to the k divided by k factorial. Just imagine k instead of x. Anyone going to tell me what series this is? I'll put over the more standard way to write it, y to the power k divided by k factorial. That would be the k equals 0. This is such a... If you remember no other series, this is the one that gives you all others. I mean, seriously, this gives you sine, cosine, all the others if you substitute in the correct thing. What is the sum of this series? It works for all y. This one is not sine because sine has a funny only the odd terms and it has a switcheroo of the sign. So this is not exactly sine. You can get it using substituting x plus I y. Yeah, that's how you get sine. But this summation is not sine of y. It's something different. Please say it out loud. If you differentiate this series, you get sum of k y to the k minus 1 divided by k minus... So that ends up being sum of y to the k minus 1 divided by k minus 1 factorial. So if you differentiate it, you actually get the same thing. So given that this is a series whose derivative is the same thing, what function is it? Anyone remember? It's a function of y. E to the y. Yep. E to the y up to a constant is the only function. So this is 1 plus y squared over 2 plus y cubed over 6 plus so on. That is e to the y. So in this context, I substitute in that with e to the power where that is the y. E to the power e to the t lambda. So it's a funny thing. It's exactly that. I can simplify e to the power lambda times e to the t minus 1. Now that is the MGF of a Poisson. It's a nice... It's a nice exercise in MGFs that we've just done, and we're not finished because we're now going to use the MGF. This is a practice in MGFs. We're going to use that to find the expected value. So to reiterate, mx of t is e to the power lambda e to the t minus 1. Now I have to differentiate that with respect to t. Mx prime of t is, well, if it was just e to the lambda x, that would be lambda e to the lambda x. But now I have to use my chain rule because instead of x I have e to the t minus 1. So I'm effectively, if it was just e to the lambda something, I get lambda e to the lambda something. Then I have to multiply by the derivative of e to the t minus 1. And that derivative of e to the t minus 1 is just e to the t. So that equals lambda e to the power lambda e to the t minus lambda plus 1. Okay. So that is a slightly strange formula. So mx prime of 0, we just substitute t equals 0 into there. So that's lambda e to the power lambda e to the 0 minus lambda plus 1. And quickly, someone, what's e to the power 0? 1. Everything to the power 0 is 1, including 0 to the 0 is 1. So e to the 0 is 1. Lambda minus lambda plus 1. So that is equal to... Okay, well, there's a shame that's happened here because I've got an error. That shouldn't... something's gone wrong. plus t. Yeah. Yeah, so I had e to the t there, and I don't know why I added plus 1. Thank you for fixing that up. Plus t. Yes, exactly right. Exactly right. And t in this context is 0. Yeah, so it's, yeah, thank you. So it does work correctly. That is lambda to the power lambda minus lambda e to the power lambda minus lambda. Now it's lambda e to the 0, which is lambda. Okay. So, and then mx double prime of 0 equals dot dot dot, and you can so that is I'm going to leave that as an exercise. You'll find that that's also lambda, and that is oh no, sorry, it's not lambda. It's lambda squared plus lambda, because that is the raw moment. The second raw moment is the second derivative of the MGF. The kth raw moment is the kth derivative of the MGF, evaluated at 0. So this is expected value of x squared equals that. And to do variance of x, so yeah, is equal to ex squared minus bx all squared equals lambda x, lambda squared plus lambda, and then you subtract lambda squared, so that equals lambda. Okay, so I'll let you finish off that. Those are the main properties of the Poisson that we need, but I'll just say, reminder, if rare, I won't even say rare, they don't have to be particularly rare. I'll just say independent, they're totally independent events, but they happen at a constant average rate. At average rate mu events, mu happenings per, I'll just say hour, but obviously it could be time, any time unit, over a period of h hours, then the number n, I'll make it lowercase h because it's not random, h hour, number n of events in that time, the time of h hours, has distribution Poisson. N is Poisson. So this is why the Poisson is so important. This is why the Poisson is so important. And you just have to, for always Poisson, the parameter is the mean. The mean number is clearly mu per hour times h hour, mu h. So lambda is not always the rate per hour, because if it's over h hours, then it's the rate per hour times the number of hours. Okay, so that's enough for Poisson. Let's go on and do more about continuous random variables. So let's have a reminder from last time about continuous random variables. Okay, a continuous random variable. Now, it seems like an indirect definition, but the most important thing about a continuous random variable is its density. So, so we're just going to define it by means of the fact that it has this density function. It has a density function. Now, it's sometimes called a probability density function, and for that reason, it's called PDF. If you see PDF, we mean density function, and that's called f subscript x. Okay, much like we called p subscript x for the probability mass function, now it's a density function, such that the key fact is the probability of x lying between 2 points A and B is, now that could be minus infinity and infinity, and it could even include a single point itself. You know, probability of equaling A is going to be 0. So this is the integral from A. Whether you include the endpoints or not is never going to make a difference because it's a continuous random variable. The density function, fx of x dx. Now it's pretty clear you want that probability to never be negative. So fx of x has to be, by definition, a density function can never be negative. Okay, so that integral should never be negative. Now you notice I didn't actually say that it has to be continuous or anything. Density functions don't have to be continuous, but it does have to be able to be integrated. So if you just there are various technicalities about what functions can and can't be integrated, and we won't even worry. It doesn't matter. We'll just write down functions, and they'll be verifiably integrable. But as an example, you might be worried about functions that are not continuous. But some functions that are not continuous, like ones that have a few jumps, are very, very tame. So if you have a few jumps, I'll even do that as our first example to say that you needn't be worried at all. So the first example of a continuous random variable is x that is going to be uniform on the interval. There's no reason to restrict to just the interval 0, 1, although you could, that's a common one, but we just do uniform on the interval a to b. So this is actually for all intervals a and b. So there's two different things that A and B are actually two different things here. Just before I was giving the general definition, you have to be able to do any interval as probability by integrating over that interval. But here I'm going to do it for a specific interval, for specific A less than B. I want it to be a decent interval on the line, so, and I don't want A to be equal to B. So A to B. Now, clearly, this has to be a probability density function, and if you recall what an integral means, that's nothing other than the area under the curve from A to B. So what this has to be is it has to be a density function. This is if we're doing y equals fx of x. It has to be a density function. The total area, it should be, and uniform means it's kind of equally likely to be anywhere in that interval, whatever that means. It means the density should be constant on that interval. So I want a constant height on this interval. The density function clearly has to then jump down to 0 away from that interval, because the probability of not being on that interval should be 0. So fx of x is then going to be the density function is going to be, it has to be a certain constant on the interval a to b. And so I'm just going to give it as a two-way option, certain constant there, and it's going to be 0 otherwise. Now, can someone tell me what the constant has to be? Because there is an important constraint. 1 over? Exactly, thank you. Yeah, many people. 1 over b minus a. Has to be constraint, and that comes from the constraint. Any probability density function, much like a mass function had to add to 1, a probability density function has to integrate to 1. So remember, I'm writing integral minus infinity to infinity fx of x dx, but that includes frequently the end, like, there's nothing wrong with writing minus infinity to infinity of fx, because that's 0 off a certain interval. So that equals 1. And then in this context, that equals minus a, not minus a, equals from a to b of a constant, whatever the constant is, dx, is c times b minus a. So if we don't know what the constant is to begin with, we just want it to be uniform, then we just, so c times b minus a is 1, so c does have to be 1 over b minus a. That's because we made the assumption of a constant density. That's what uniform is. There are many other random variables that don't have constant density, and then they have whatever density they have. But the probability that x is in a different interval, c to d, is then, it actually depends, because if c and d, you'd like to say that you just imagine c to d being like that. If c to d lie within the interval a to b, then it is exactly what you'd expect. It is c, well, it's integral from c to d of 1 over b minus a dx, which is, of course, d minus c divided by b minus a. But that is so long as c has to be, at least a, and c should be less than d, and d has to be at most b. If that's not the case, you've run off the edge. So if that's, if you tried to do from a c that was less, you would just replace it with a. So, okay. So d minus c. Now this should seem totally reasonable, because d minus c is a certain fraction of the length that you're interested in, the favourable one, and then divide by the total length. So uniform is pretty predictable. Now let us talk about cumulative distribution functions, because while they're not the be-all and end-all, they are, and by the way, a uniform on an interval of length 1, particularly 0 to 1, that has constant density 1, so that's kind of a nice one that we often use, uniform 0, 1. Let's talk about the cumulative distribution function. We did define this once before. distribution function of any, now this doesn't have to be a continuous random variable, but any random variable x is the function, and we have a fairly standard notation for it, capital F. Lowercase f for density, capital F for cumulative distribution function, and CDF is the abbreviation. We have PMF, PDF, and now we have CDF. Note it's called the distribution function, not the density function. It is just the chance of being less than or equal to x, and that's a convention. Why don't we do greater than or equal? Just because that's something that's easy to do, and that way we're always consistent. But you know, you could equally consider the other side. But we always, for the conventional name of CDF, we always do the probability of the left tail, less than or equal to x. So clearly, if you do have a density function, and now I'm just going to have a typical density function rather than the uniform density function, this is clearly the area under the curve all the way from, you might as well say, minus infinity up to x. So in the context of continuous, so that's the definition of the cumulative distribution function. That works for any random variable. Okay? But for f continuous, okay, for a continuous random variable, no, for x a continuous random variable, and x a continuous random variable, fx of x is equal to the integral from minus infinity to little x of the density function, little f x dx. Okay, so now, once again, let's just do this in the example of the uniform. I also, convention for notation, because this, much like we don't want to have to give all these options of either this or 0, for probability density function, if we write fx of x equals some value, dot, 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 you know, comma, you know, a less than x less than b. If I give some range, we mean, so if we write this, we mean something slightly more long-winded, which is, you know, if it's not on that interval, if it hasn't been specified, then it should be 0. It means that thing if a is less than x, less than b, and 0 otherwise. Okay? So that's a shortcut for specifying intervals. Thus, and I'll give the example later. And for CDF, there's a similar convention, but it's not the same. If we write capital Fx of x is something, so once again, a less than x less than b, we mean, and it doesn't have to be two-sided, it could be one-sided, capital Fx of x is equal to the same thing if you're on that range. And it means that the chance of being, it means that this is the only range that matters, and therefore the chance of being to the left of a is 0, because I only care about a to b. So 0 if x is less than or equal to a. And it means that it's 1 if x is greater than or equal to b. So the convention is to omit the several cases, which makes it long-winded. And the way you do that convention is for density, it just means it's 0 everywhere that you don't mention. For CDF, it's slightly different. It's 0 to the left, it's 1 to the right. And that gets back to the facts about all CDFs. And if you like, this is actually a characterization. Much like we characterized all PMFs, as in saying everything that every PMF is of this form and everything of this form is a PMF. This is the corresponding characterization about CDFs. It's slightly complicated, so I'm sorry about that. But the main things are that f of, so it doesn't matter what variable, just f of x always has to be between 0 and 1. That'll actually be, that's slightly redundant because that will follow from what we say. F is a non-decreasing function. Okay. I know that's kind of a strange word, but can someone just tell me what the word non-decreasing means? How is it different from increasing? Increasing or constant, that's fine. So it could be constant on some small interval and then keep going up later. So Sometimes people say weakly increasing in that it could go up or stay the same at any point, but it never goes down. So that means, another way of saying that, x less than y implies fx less than or equal to f of y. And the limit as x goes to minus infinity of f of x has to be equal to 0. Can anyone tell me why that has to be the case? For any remember, I just, in case you forgot, CDF is always the chance of the variable. It's nothing other than probability that capital X is less than or equal to little x. That's always what it is. That's the definition of a CDF. So why is it then necessary that a CDF must tend to 0 as you go to minus infinity? Informally, what is, like, if I did f of minus infinity kind of informally, what does that mean? It's like the chance of being less than or equal to minus infinity. You can't do that because it has to be a random real number. So none of the values will be less than or equal to minus infinity. And for a similar reason, the probability of being less than infinity, well, any real number is less than infinity. So informally, you can see that because we're assuming it's a random variable that doesn't actually equal minus infinity, anything silly like that. It's just, and it never actually equals infinity. It's always an actual real number between those limits. So that's why it's useful to take these as the total endpoints. That's important because frequently it can, it has a long tail. It can theoretically take large and large values, but can't take the actual value of infinity. So, and then there's, unfortunately, that would be nice, all those make sense. There's a final little property which is f is right continuous, okay? Now, it's not always, okay. So this is the characterization. And I'll even say, that's true, it is slightly redundant in the characterization, because once you know it's increasing, if you know it's increasing with left limit 0 and right limit 1, then you know it's between 0 and 1, so that's slightly redundant. But f is right continuous. What that means is the limit as y goes to x from above, from the right, of f of y equals f of x. And that's for all x. Okay. That's, okay, once again, it's a bit like this thing. What's the chance of being less than or equal to y? Well, that's the same as being the chance of less than or equal to every x that's bigger than y. It's not the same from the left, because you could have a chance of being exactly on, like if you're thinking about a discrete random variable, like a geometric, it has a chance of being 1. So the chance of being less than or equal to 1 is positive, but the chance of being less than or equal to 0.999 is 0. Geometric is always bigger than 1. So it's only right continuous. So if it's discrete, it's not going to be a left continuous function. So this characterization is now complete. But it is also another fact, and this sort of motivates the name. Fact about another fact. This is not the characterization. This is just another fact. If x is a continuous random variable, then f subscript x is continuous. Okay. And now here's a funny thing I'm going to say, and maybe this is, we're going to say a little bit, I'll finish that fact later. Let's do our, get back to the exam. I'm focusing on uniform because it's so simple and you can see all the relevant features at that point. So x is uniform, and let's make it our life even easier on ourselves. Make it 0 to 1. It just makes the calculations, the numbers simpler. X is going to be uniform 0 to 1. So then we write fx of x equals, I'm actually going to write 1 comma x between 0 and 1. Okay? Now, I consider that to be a complete description. Remember my convention? Especially if I've written a density that integrates to 1. This is, here's our density function. And you might ask, why did I include the endpoints versus excluding them? That actually, at a jump, you can decide either way, whether you include endpoints or exclude them. So here is the density function of this. This is x0, x1, right? So that y equals fx of x. I'm going to have to complain about that door. So That's your density function. And remember I said density functions don't have to be continuous. They just have to be able to be integrated. Now this is a classic example. This is not continuous at 0, it's not continuous at 1. Those jumps don't present any problem for integrating because integrals talk about area under the curve, and there's no problem, you know, the area under the curve just starts increasing at 0. So let's, so I just, you know, recall, I'll just say brackets here, recall the convention that I just did on a page ago. The convention about notation I consider quite important because it saves me from, you see, I consider this a full description of it. I don't have to say that the density is 0 elsewhere. It went without saying. So just in case that wasn't clear. So now, using the convention also for the CDF of this x, so with this example, capital Fx of x, well, it is, of course, the probability of being, once again, I'm going to content myself to be interested in the range of values between 0 and 1. Because what's the chance that this uniform lies somewhere between 0 and 1 with probability 1. So the chance of being negative is 0. The chance of being bigger than 1 is 1. So those are uninteresting. I focus on the interesting segment. So 0 less than or equal to x less than or equal to 1. If you're worried about whether I include equal signs here or here, it's totally irrelevant. So don't worry about that. Totally irrelevant. So you could do either. Now I just need to find, it's the probability that x is, capital X is less than or equal to x. So I have to integrate the density function from minus infinity to x. But just watch what I do. I don't want to write, I'm going to substitute in what the density function is, right? The density is 1, but I'm not going to write the integral from minus infinity to x of 1. Because the density is not 1 at minus infinity. It's only 1 on the relevant region. So it'll be quite common that you have this relevant interval, okay? And outside that relevant interval, the density will be 0 outside that relevant interval. So we just want to focus on that, and that means I only integrate the density from 0 to x. Do you see that? Even though the general formula, I do have this general formula that you recall, the general formula for a continuous random variable is integrate minus infinity to x. But use your common sense. If it's a density that only exists from 0 onwards, we only integrate from 0. So just use your common sense. Okay, so 1 times dx. Okay, so that's a very easy integral. Integral of 1 is x. Well, you know, dummy variable t evaluated from 0 to 1, so I'll let you do the integral yourself. It is exactly x, comma. Okay. So I'll just say here, it went without saying. This just saves us time, that fx of x is 0 for x less than 0 and is 1 for x bigger than 1. Okay, that's just totally obvious and we don't bother to say it. Okay, so we have the CDF. Let us draw the CDF. So this is the graph of the PDF, and the graph of the CDF is this function x from 0 to 1. Now, okay, so 0 to 1. So this, now I am graphing y equals capital F x of x. Okay, this is what I'm graphing. Now I should probably continue. We know that it's 0 to the left here, and should I jump back down to 0 for the rest of the CDF? Should I jump back down? No, CDFs don't jump down. In fact, they're always non-decreasing. As you know, it stays at 1 here. So the parts that went without saying are that part and that part. This is the part we actually have to write down. Okay, so easy. Now, what I want to... Okay, this illustrates some of the things that I want to now say as generalities about continuous random variables. Because you'll see, it's very common for people to say capital Fx prime equals little fx. And that's true sometimes, most of the time, usually even. But we should be careful about exactly which points it's at. So there's a reason, you know, capital F and lowercase f are very commonly related by a differentiable relation. At each value x at which little fx is continuous. Okay? Okay? So usually there will be not that many points where it's not continuous, right? As I said, densities don't have to be continuous everywhere. But typically, especially if you're doing this piecewise thing, typically it'll be a bit continuous, a bit continuous, a bit continuous with a few jumps. And so then you would not expect the cumulative, the CDF, to be differentiable at those jump points. It's not. And in fact, this is a classic example of a function that's not differentiable. Not differentiable there, not differentiable there. If you want to really get into the weeds, you can talk about a right derivative and a left derivative. So at 0, it has a right derivative, which is 1, and a left derivative, which is 0. At 1, it has a right derivative, which is 1, and a left derivative, that is 0. So those are kind of unimportant for us, because for us, I actually think this can be useful for finding the PDF given the CDF. So to get from density to cumulative, you integrate. To get from cumulative CDF to density, you differentiate. So that's things. But you just are wary that there might be 1 or 2 points where it's not continuous. And therefore, at the points where CDF is not, at the points where the PDF is not continuous, you don't expect to be able to differentiate. Okay, that's all about that. Now, we really do need to go on and talk about expectations of continuous random variables. So, of continuous random variables. Now, there's a whole menagerie of important continuous random variables which we'll start talking about next time. But really, it's important to understand the underlying principles first. So, the expectation, recall, the expectation of every variable has already been defined, but the definition was not I'll say in an impractical way. Just it was a definition to show you that the unity of the definition across all areas of probability, but it has been defined in an impractical way. If x is, we just imagine a random variable that's always non-negative, like that uniform that we did, then expected value of x is, we have this funny definition, limit as y tends to x upwards, it has to be y is less than or equal to the expected value of y, for all all random variables y, they have to be less than or x, that take a finite number of values. So this is even better than discrete. Just discrete with finitely many values. Okay, so this is in brackets. I'm saying that this is a definition that is so unwieldy you'd never actually use it in practice, but it unifies all concepts of random variables, including there are even more exotic ones that are not discrete or continuous. It's always the same. And if it was negative, you just do the positive part minus the negative part. So now I'm going to say that this is a theorem. Now this is nice because it applies not only to random variables themselves, but also any function of those random variables. But I'll do it in 2 parts. Okay. First of all, so that the expected value of x is equal to the integral. Okay, so this is if x is continuous with density with PDF. Remember, PDF is synonymous with density. I will warn you, the typed notes that you find on the website use PDF and PMF the same. Like they call it PDF even for discrete. I don't like that. I like to keep discrete with PMF, mass function, and continuous with PDF, density function. With PDF, capital F x of x, and let's say that it's from a less than x less than b. That's nice because then I'll be able to write the integrals in the same region, a to b. Now, this does not rule out a equals minus infinity or b equals infinity. So continuous variables are allowed to go off to infinity in both directions, or they are allowed to be bounded in one direction or both directions. So all of those are possibilities, and the formula is always the same. X, f of x dx. Okay, so that's the formula, but I just want to be clear that that's not the definition. And the much like there was a proviso we actually did that example of a Cauchy random variable where you had very, very large positives and very, very large negatives, and they were so wild that effectively there was no expectation. So I'll just put this as an asterisk. So long as, this is the same as that absolute convergence I talked about, so long as the integral a to b of absolute value of x, fx of x dx is finite. Okay, so I put it as an asterisk because it's not so important. The only way that could happen is if a equals minus infinity or b equals infinity, because if it's just in a finite region, there's no way it can be less than minus a or bigger than b. But if it does go off to infinity, then it could be. But there's also expected value of the function of continuous random variable. Maybe we'll talk more about that later when it's when we talk about transformations. But it's the same thing, because you just think if x goes from a to b, you have g of x, fx of x dx. And how do you think about that? This is the way you think about that. That is the probability that x lies in this little interval from x to x plus dx. That's the way you should think about it. So much like all expectations, it's always a weighted average. Okay, and I'll put the asterisk on this as well. G of x. It's always a weighted average. So just think the expected value of x is the average over all values of x weighted by their probability, and their probability is represented by the density. And the expected value of g of x is the integral over all values of x weighted by their all values of x. You do the target that you want, g of x, times the probability of being in that range, which is density dx. And then because it's a continuous random variable, you have to do an integral instead of a sum, which we did in the discrete case. So that theorem, I think I'm not going to prove in this course. It's it does follow from this definition. There's a little bit of coming out with an approximating. Effectively, you approximate your continuous random variable by a discrete one, more or less. Effectively, you could think of round it down to the nearest tenth, and then round it down to the nearest 100th, round it down to the nearest 1,000. That actually works. So anyway, so that follows from all the things we need to do before, and that can easily calculate things. So let's finish the example. And by the way, although I haven't explicitly talked about the variance of a continuous random variable, we know what variance is in general. And by the way, Chebyshev also works in general. We know what variance is in general. We can just use these formulas to to do that. So let's just finish with uniform 0 to 1. Expected value of x is equal to the integral. Now, in principle, by the way, when I say a to b, often you'll see this formula stated with minus infinity to infinity. That will be the case for a density that goes from minus infinity to infinity. So you always just have to put the appropriate limits of integration here for your variable. So in this case, the appropriate limits are 0 to 1 x dx. I forgot, let's be very clear about it. The 1, x times 1 dx, that is the density. Okay? I just put in the letter 1, the 1 there to show I've done x times the density dx. Okay, and that is integral of x dx is x squared over 2. You can do the calculation yourself. The expected value is 1/2. Now this shouldn't be a surprise because it's kind of symmetrical around 1/2. In fact, whenever you have a symmetrical random variable with an axis of symmetry, the expectation, if it exists, must be that axis of symmetry. We had an interesting example of the Cauchy random variable. We might talk about it again later with this random angle tangent. That actually is symmetric around 0, but the expectation doesn't exist because it's infinity minus infinity. But if it does exist, then it has to be at the axis of symmetry, if there exists an axis of symmetry. So let's also find variance of x, because there's nothing wrong with variance of x. That's expected x squared minus mean squared, remember? So I'm going to be doing integral 0 to 1. Calculating expected value of x squared is easy. I use this formula. See? G of x equals x squared. So I just put in x squared times density times the x. Easy as pie. I'm just using the second of those two formulas. So that's x integral of x squared is x cubed divided by 3. Oh, I have to subtract off 1/2 squared. So that's 1/3. X cubed over 3 evaluated from 0 to 1 is 1/3